Right, so the first question asks about sound waves being mechanical waves, and the diagram shows the disturbance of air particles in the path of a sound wave at an instant in time. So we've got point A here, point B, and point C, and this is the direction that the energy is transferring, so it's going from here to here. Which label arrowed A, B, or C correctly identifies the wavelength? Well, it has to be from the same identical point. So in the center here is the center of a compression, and this is the center of the next compression, so that is the wavelength. So the wavelength is from one compression to the next. So let's just label this. This is called a compression, and the reason for that is because the air particles have compressed together. This part here is called a rarefaction, and what does that mean? It means the air particles have spread apart. So we could go from a rarefaction to a rarefaction, that would be the wavelength, or we could go from a compression to a compression. So we go from the center to the center. So which one is it? It is B. What type of wave is a sound wave? It is a longitudinal wave. Remember, transverse waves are electromagnetic waves. They are light waves. So electromagnetic waves are all forms of light, from radio waves all the way down to gamma rays. Right, a student investigates the reflection of sound waves from a building. One student hits two metal bars together to produce a sound wave. So this sound wave is going to travel all the way down here, and when it gets to the building, it's going to reflect and it's going to travel all the way back. So why must the student divide the time on the stop clock by 2? Well, the reason for that is because the distance is from here to back there again. Okay, so the sound wave travels to the building and back due to reflection. Now remember, the reflection of a sound wave is called an echo. This is often asked in a GCSE paper. Right, the next question says calculate the mean of the three results. So if we have three results, what do we need to do? We just need to add the three results and then divide by how many there are. So 0.33 plus 0.27 plus 0.3, and that will give you 0.9. There are three results, three trials, so we divide by 3, and that will give you 0.3. So the mean is 0.3. Okay, the next question says the time taken for the sound wave to reach the building from different distances is shown in the graph. Use the mean time. Well, we just said that was 0.3. That's what we just calculated. So we're going to go up from 0.3 and across, and that equals 100 meters. Okay, the student sees differences between the results. Choose one improvement the student could make to the investigation. Right, decrease the distance between the students and the building. Well, if we did that, that would make it a bigger error. The more distance the sound wave travels, the longer it's going to take for that to happen. So that's going to make the error lower. If you have a bigger distance, then the time taken will be a greater time, and therefore that's a better thing to do. So having a smaller distance is going to make the timing a lot more difficult. So that's going to make a bigger error. Playing a long note on a musical instrument instead of using metal bars, well, that's not going to make much difference at all. So we need to use a data logger. Right, how does the amplitude of the echo compare with the amplitude of the sound wave produced by the metal bar? Well, if the echo is quieter, then the amplitude has to be lower. Remember, this is a quiet sound, and a loud sound has a larger amplitude. So the amplitude of a quiet sound is lower. Right, you want to hear the reflection echo. Remember, echo is the reflection of a sound wave of the ticking watch through the tube. Which is the best position to put the tube? Well, remember, it's reflecting, so our law of reflection states that if we draw a normal line, it will reflect at the same angle. Now remember, when we measure it, it's this angle. So this is the angle of incidence, and this is the angle of reflection. So that means it's going to travel down E. Waves are produced on the surface of the water. You can see there is one wave to there. second wave, third wave, fourth wave. So how many waves have we got? We've got 4 waves, and there is 10 centimeters for the 4 waves. So if we divide 10 by 4, we get the length of one wave. So that's 2.5 plus 2.5 plus 2.5 plus 2.5, and that equals 10. So each one is 2.5 centimeters. So that means that 2.5 times 4 would give us the whole thing. Right, after testing the scale model, a full-size boat is built. The boat is tested at sea. Calculate the speed of the water waves. So the speed of any wave, so wave speed is equal to the wavelength multiplied by the frequency. So what's the wavelength? 6 meters. I'm going to multiply that by the frequency in hertz of 0.5, and that will give us 3 meters per second. So I'll just put wave speed there. So wave speed is equal to wavelength times frequency. Or V, which is the wave speed, is equal to lambda, which is the wavelength, times F. So you'll often see this as symbols, and that's what those symbols mean. V is the wave speed, lambda is the Greek symbol for wavelength, and F is the symbol for frequency. Suggests why a scale model is tested before the full size one. Well, it's about cost, so obviously that one would be cheaper. Right, the diagram shows a ray of light travelling through a glass block. So remember, this is transparent, so it is going to come out the other side. This isn't a mirror, it's going to come out the other side. It says complete the diagram to show what happens to the right ray when it comes out of the glass. Well, it's going from glass, which is a solid, and it's going into air, which is a gas. So what's going to happen? Well, when it goes from a solid to a gas, it's going to speed up. So the light's going to travel faster through a gas than it will through a solid. So when it speeds up, this angle here is going to be less than the refracted angle. So we just need to make sure that the angle is going to be produced is greater. So we carried that normal line on just to show it. This angle should be larger. So it's going to refract away from the normal line. So you just need to make sure that it refracts away from normal line. So just to explain that, if we have a glass block and the light hits the block, we draw a normal line. Because it's going from a gas to a solid, it'd do the opposite this time, and that would move towards it. And then if we drew another normal line where it leaves, it would move away. So when light hits a block, it refracts towards the normal line. When it leaves, it refracts away from the normal line. So that is the refraction when it's at an angle. Remember, any light that passes straight through that follows the normal line will not refract, because the whole wave will change speed at the same time. So it will all slow down and then it will all speed up again. Right, explain why this happens to the ray of light. There is a change in speed. And what is that change of speed? Well, remember, it's gone from a solid to a gas, so it has caused it to speed up. Right, so this shows a plane mirror. Remember, if we were to draw this, we would have a normal line there. But it's not asking us about reflection, it's going to ask us about refraction again. So this is back to that drawing we've just had. Whatever angle this is, can you see that that angle is smaller? That means it is refracted towards the normal line. Remember, we've gone from a gas. So if this is our block and we draw a normal line, and the light goes into the block, it refracts towards the normal line. If we draw another normal line, it will refract back away. Now this angle has to be the same as this angle. So when we draw this one, we should really measure this with a protractor, and then we would measure that angle. That one and that one should be the same. So if this angle here is 35 degrees, that angle has to be 35 degrees, and this angle has to be less than 35 because it's refracted here towards the normal line, because it's gone from a gas to a solid, and when it leaves, it's going to travel at exactly the same speed it was going, so it refracts back out by the same amount. Name the dashed line. Well, this dashed line is called the normal line. And the normal line is just an imaginary line that we draw at 90 degrees to the object. and it's just to symbolize where the light is hitting the block. It's so we can calculate the angle from the normal line. We always measure the angle from the normal line, which is just an imaginary line where the light hits at 90 degrees to the object. Okay, the next question asks us to draw a line of best fit. So starting from here, we've got a line through the points as carefully as possible. Remember, you must do this with a pencil, a sharp pencil, and you can see we've got a nice line of best fit. Use figure 3 to describe the relationship. Well, we first of all see how many it's out of. It's out of 2, so we need 2 points here. So what's the first thing we do? We talk about how changing the independent variable affects the dependent variable. So when we move this way, we are increasing the independent variable. So increasing, well, what is the independent variable? We just state what is on the axis. Increasing the angle of incidence. So we've stated that, and then we talk about what's happening in our dependent. Well, that's also increasing. So increasing the angle of incidence increases the angle of refraction. So that's a really simple statement using our independent variable and our dependent variable. So that's how we start every graph. We talk about how changing the independent variable affects the dependent variable. Now the next point, so we've talked about that, we need to give a more specific part of this graph. Well, it's not a straight line, so we can say it is not directly proportional. Remember, if it was directly proportional, the line would just go straight on, and that's not happening. We've got a curve, so it is not directly proportional. Right, the next question says place the parts in order of increasing energy. Well, what has the most energy? Gamma. What has the least energy? Infrared. And in the middle we've got visible light. So that's these 3 parts here. Right, draw a ring around the correct answer to complete each sentence. The number of waves passing a point in 1 second is called the frequency. Remember, frequency is the number of waves per second. So if this was the number of waves and this was in 1 second, we would have 1 wave to there, 2 waves to there, 3 waves to there, and 4 waves. There would be 4 waves per second. That means a frequency of 4 Hertz. All parts of the electromagnetic spectrum travel at the same speed through a vacuum. And what is that speed? You have to know that it's 3 times 10 to the 8 meters per second. Right, the next question is about uses for communication. So how is infrared used for communication? Well, it's used in remote controls. So any remote you use for changing channel, the TV, for the projector in your schools, that uses an infrared source. Microwaves for communication, well, remember when we communicate with satellites in space, we send microwaves. Why do we send microwaves? Because they can penetrate through the atmosphere. Remember, it's actually called the ionosphere. So microwaves are really useful for satellite communication because they can penetrate the ionosphere. So we use these for satellites. So that could be satellite TV or for GPS, and we also use them for mobile phones. So mobile phones use microwaves to transmit waves from one phone to another one. Radio waves, well, that could be TV. Okay, and while we're talking about the ionosphere, remember, if I just change this pen color, that radio waves are actually able to reflect off the ionosphere, and you're often asked to draw diagrams for this. So if we zoomed in on this diagram and this was the Earth and this represented the ionosphere, you could actually send a radio wave up into the ionosphere from one place to another place. And how does it reflect? Well, it uses the law of reflection, where the angle of incidence is always equal to the angle of reflection. So when you're reflecting radio waves, you can reflect them off the ionosphere, and the ionosphere is the charged part of the atmosphere. What about visible light? Well, all the cables that connect your router, your internet router in your house, use visible light, and that is fiber optics. Fiber optics are high-speed internet, so that is for the internet. So you've got fiber optic cables that transmit the internet at very fast speeds, then you're using visible light which transmits down a fiber optic cable. Right, the next question is not specifically on the new specification, so I'm going to ignore this question because convection, conduction and radiation aren't actually on the specification. In terms of this question, I'm just going to talk about a data logger because this is the kind of how science works question that you could be asked. It says, give 2 advantages of using a data logger. Now, a data logger is just a digital thermometer, in this particular case, that can be left running. Why is that useful? Because you don't have to keep taking the temperature. You could leave it on for a whole week and it would take the temperature constantly and plot a graph for a week, so you don't have to keep taking the temperature. So why is that useful? Well, obviously you don't have to keep taking the temperature. What else is better about this? Well, if you look at the scale, you can see it's quite hard to see the difference between 80 and 90, whereas this one has got a much higher resolution. Now remember, resolution is the scale, so 0.40 tells you that the resolution goes down to 0.01 degrees C of resolution. So the resolution is the accuracy of the scale. So what is the main advantage? Well, one is it's got a higher resolution. Sorry, spell this word correctly. Resolution. And that means the scale, so it's got a higher resolution in degrees C, which makes the reading more accurate. The other one is that it can take a reading continuously. So it's obviously going to be really helpful if you can take a continuous reading, because you don't have to keep going back to the thermometer. Right, the next question says, explain the difference in temperature between the water in the 2 cans. Now again, this is really not on the specification anymore, but if you're doing triple science, you do need to know about the effects of radiation between colour. So black is actually a better emitter of radiation. So you can see the temperature of the black can has gone down more than the temperature of the white can. I'm just going to do that in a different colour. So this temperature here is of the white can, the end temperature is around 50 degrees. And the temperature of the black can's gone down to 20 degrees. So why has that happened? Because black is a better emitter of infrared. I'm just going to put IR for infrared radiation. And infrared radiation is just heat. So it's giving out more heat. The black can, because black is a better emitter, will give out more can. So that give out more radiation, sorry, and that means it will cool down faster than the other can. So black is a better emitter of IR radiation, so cools faster. Right, the next one says, on the graph draw a line for the results you would expect for the can if it was painted grey. So grey is kind of between the two, because grey is darker than white, and the darker the colour, the better it is going to be at emitting. But it's not as dark as black, so it's not going to emit as much as black. So I'm going to start at the same temperature. Let's go back again, sorry. I'm going to start at the same temperature, but it's going to be somewhere between the two, and that is going to be the grey one. So we make sure we label it so it's really clear. And if you use the pencil, you could go over it with a different coloured pen, and then you make sure that the examiner knows exactly where you're at. But the first time, always draw it with a pencil. In case you make a mistake, then you can rub it out. Right, carrying on. So we've got the electromagnetic spectrum, and be careful because you can clearly see they've flipped it here. So this has got the highest energy gamma rays over here and the lowest energy radio waves there. So this is low energy and this is high energy. Remember, these have got a very small wavelength and these have got a large. I'm just going to write large wavelength as well. And you have to learn that for your exam. So the wavelength of a radio wave is really long. Right, so name a part of the electromagnetic spectrum with a longer wavelength than microwaves. Well, longer is that way, so that must be a radio wave. A greater energy than X-rays, well, these have got the highest energy, so that means it's gamma. A higher frequency than ultraviolet, well, that would be either of these two, because the frequency, the number of waves as you go this way, gets greater and greater. So that could either be an X-ray or a gamma ray. Right, the next question is about describing a wave. So how many waves are shown in the diagram? Well, we go up and down and back to where we started, which is there, up, down, back to where we started. So there are 2 waves in the diagram. What is the wavelength of each wave in the diagram? So from here to here, you can see that is a distance of 4, but that is 4 centimeters. And what is the amplitude of the wave? That is half the height, so it's from there to there, and that is 2 centimeters. Right, complete the sentence below. The oscillations of the wave in the diagram are perpendicular to the direction of energy transfer. They are called transverse waves. Remember, this is a transverse wave, and you can see that because it's going up and down. So the vibration, the oscillation goes up and down, and the energy travels that way. And remember, I said that this makes a T for transverse. Right, draw a ring around the correct answer in the box to complete each sentences. Light waves are transverse and sound waves are longitudinal. Right, diagrams A, B, C and D show oscilloscope traces of 4 different sound waves. The oscilloscope settings are the same each time. Give the letter of the loudest sound. Well, the sound wave is to do with the amplitude, and this has got the greatest amplitude as it's got the largest height from the center, so that must be B. Give the letter of the highest pitch sound. That is the one with the most waves per second. This one has got 1, 2, 3, 4, 5, 6, 7 waves per second. So the answer is D. Remember, this one would just have 1 wave, 2 waves per second. Right, a ripple tank. Remember, you've done a practical or you've watched a practical where a ripple tank created waves in a tray, and you could watch the water waves moving up and down and calculate the frequency, the wavelength and the wave speed of the water wave. What is the wavelength of each wave in this diagram? Right, so the wavelength is from there to, so we go down and back to where we started. So that's 1 wave, 2 waves, 3 waves. So if the whole of 3 waves is 6, then we're going to divide that by 3, and that will give us 2 centimeters. The ripple tank produces 10 waves in 2 seconds. So if we've got 10 waves and it's taken 2 seconds, we're going to divide by 2. So frequency is the number of waves per second. So this is 10 waves. There are 10 waves, and it's per the time taken. So it's not in 1 second this time. We're not dividing by 1. It's in 2 seconds. So it's number of waves divided by the time taken. 10 waves, 2 seconds taken. Frequency is equal to 5. Okay, the bar is made to move faster, and it produces waves with a frequency of 20 Hertz this time. So what we're going to do, well, wave speed, which I'm just going to give a letter V, is equal to frequency times the wavelength. So what is our frequency? It's 20. What is our wavelength? It's 0.5 centimeters. Now be careful, in this particular question the unit is in centimeters per second. But if that was in meters per second, we would have to convert this. In this question we don't have to do that. So what's 20 times 0.5? Well, that's equal to 10, and the unit is given. Okay, in this next question, the last question, there's a graph that we need to complete, which starts here at the origin, and it says there is 1 anomalous result. So we need to look, right, if we were to plot this graph, it would look something like that. So the anomalous result is the one that it does not fit with the line of best fit. So where is something under the line of best fit? Well, it's that one, so we know we're not going to include this. So we're going to draw a ring around that anomalous result. Remember, anomalous result doesn't fit a pattern. That is the definition of an anomalous result. It doesn't fit a pattern, or we just draw this line of best fit. Now remember, you must do this with a pencil. it lies away from the line of best fit. So one that doesn't fit with the line of best fit is also an anomalous result. Use your line of best fit to find the speed of the wave at a depth of 20 centimeters. So obviously we need to continue this graph on. We would expect if this curve continues that this would flatten off. It would something like that. So at 20, this is where the line is there. So if we continue that on to the speed, then it's somewhere over there. You would obviously use a ruler, and it looks like it's at 3.5. So the wave speed is 3.5 centimeters per second. So that unit really should be over here, and that's centimeters per second. Right, the following parts are just the answers. So if you just move straight to the answers, I will leave these on for a few seconds.